Hello everyone, I'm Alex Cole and I'm with the Canadian Wildlife Federation. And today I'm going to explain how we went about answering this question. How effective are fisheries closures? And when I say effective, what I mean is their ability to reduce entanglement risk and to what amount. So in Canada, fisheries closures have been in place for the last 5 years as a management measure aimed at reducing entanglement risk to right whales, but the protocols for establishing those closures have changed in each year. This led us to wonder what the differences were from year to year and from protocol to protocol. Has one closure strategy been more effective than another? What's the overall amount of risk that's been removed to date? To answer these, we conducted an orthogonal risk analysis of the closure protocols from 2018 through 2021 in the southern Gulf of St. Lawrence snow crab fishery. We chose this fishery because it's a priority focus of these closures. To start, I want to define risk as we use it. So we define entanglement risk as the probability of co-occurrence of fishing gear and whales in time and space. While true risk follows this process, so co-occurrence followed by contact resulting in an entanglement, and then the severity of the outcome. At this time, there's not enough reasonable estimates of these other probabilities to include in a risk estimate. But the probability of an entanglement given co-occurrence is constant within an entanglement event. So co-occurrence must be a direct function of risk and can be used as a proxy. Similarly, we know that entanglements don't need to be lethal to cause harm, so it's not unreasonable to assume all entanglements are equally bad and to be avoided. So we also assume the consequence is a constant. So at last year's meeting, I presented our methods of how we calculated a baseline entanglement risk, so I'm not going to talk about that today, but I did want to show what that risk layer looks like since it's a starting point of our analysis. And these maps show the relative probability of entanglement for the snow crab fishery during May on the left and June on the right if fishing were to continue as it was pre-2018 before closures were implemented. And the warm colors represent the areas of higher risk. So now that we have a baseline level of risk, the next step is to create the closure scenarios. So we used annual whale detections for 2018 through 2021 to trigger closures following each of the closure protocols. And these are the real-time detections that are used in real life, so this lets us be as accurate as possible. We did this for each whale detection pattern and each closure protocol, giving us 16 independent scenarios. And this is where the orthogonal side of this analysis comes into play. So having these independent treatments lets us compare how each closure protocol would perform under different whale distributions, how each annual protocol compared across the same whale distribution, and the real life value where the annual whale distribution and closure protocol are what actually happened. So once we have all the closed grid cells for each treatment, we're able to calculate the amount of risk removed in each scenario. So to get to this number, we incorporated 3 important considerations. First is a graded gear removal phase. So when a closure is announced, harvesters are given a minimum of 48 hours to remove their gear before the cell is to be gear-free. And we looked at the length of the gear removal phase from the closure announcements and found that 3 days was the average length of time given. Then, looking at the fisheries logbook data, we found that gear was removed at a fairly constant rate. So we applied a 3-day gear removal phase before each closure where gear, and thus risk, was removed in equal amounts. So for example, 3 days before a closure, a third of the risk is removed. 2 days before, 2/3 is removed. And we did not apply this to the static closures used in the 2018 and 2019 protocols because no fishing took place before they came into effect, so there was nothing to remove. So second, we left behind 5% of the risk in the closed areas to account for lost gear. And we received information from the DFO lost gear reporting system and estimated that over the last 4 years, on average, 3% of the annual fishing gear in this fishery is lost. So we chose 5% to allow for considerations for historic lost gear and gaps in reporting, giving us a slightly more conservative estimate. And same as before, we did not apply this to the static closures. And then third, we account for the redistribution of gear from a closed cell to the areas that are open to fishing. And this is what we refer to as displaced gear. With this, we aren't changing the number of end lines, just where they are. So we previously published a paper on this and found that the relocation of gear is really difficult to accurately predict. To simplify it for this assessment, we equally distributed displaced gear across all areas where fishing could still take place. And then we also did this for the gear removal phase. So the risk removed by the closures is the sum of the risk in both closed cells and those cells in the gear removal phase. And the total percentage of risk reduced is the difference between the remaining risk outside the closures as it compares to that baseline with no closures. So back to our original question, how effective are the closures? Are any of the protocols more effective than another? So we used ANOVA and post-hoc tests on the estimated risk reduction values between the orthogonal groups, and those results are shown here. Each row is a comparison of the different closure protocols across the same whale distribution, where larger reductions resulting in significant difference are indicated with the greater than symbol. For example, the first row is the 2018 whale distribution pattern, where results indicate that the 2018 protocol had a larger risk reduction with significant differences from the others. And overall, you can see there are some differences in our results across the different whale distributions. But while there is the potential for higher risk reduction with some of the protocols, these results were not convincing enough to show differences among them. And based on this limited sample, it seems like each of the protocols are currently performing equally effectively in the southern Gulf of St. Lawrence snow crab fishery. As for the amount of risk that's been removed to date, we need to look along the diagonal of that table I showed earlier, which is the real life closures. And we see that the level of risk reduction has been consistent from year to year. And statistically, there are no differences among these years, so there has not been a significant change. This leaves us with an average of 62% of the entanglement risk from the snow crab fishery removed since 2018. Although statistically there is no difference in the level of risk reduction among the years, you can see that the annual risk removed has some variability despite large changes in the closure protocols. I haven't shown the difference in the number of cells closed in this presentation, but more areas are closed by the 2020 and 2021 protocols. But these closures often happen in grid cells where there's no risk value, which means in our baseline risk, there's no co-occurrence in those grid cells for this fishery. And we cannot give credit for these areas in this fishery if there was never any risk there to begin with. What this indicates is that the whale distribution is an important driving factor in the effectiveness of risk reduction, and it could be that we're now finding whales more often in areas outside the active fishery. This could also explain the variability we see on that previous slide. So to conclude with a few thoughts. First, although we are accounting for numerous factors such as lost gear and the redistribution of displaced gear, there are assumptions inherent in each of these predictions. Real-life closures and implementations can be more variable. And we are also only examining the southern Gulf of St. Lawrence snow crab fishery in this assessment. We also don't make considerations for other management measures such as early season start dates or on-demand gear that can further reduce co-occurrence. But I do want to note that on-demand gear only accomplishes this if these systems are used to replace traditional gear and reduce the number of end lines in the water. On the other hand, we don't account for other gear modifications such as weak gear because we're concerned with the prevention of entanglements rather than alleviation methods. But ultimately, our results do show that these fisheries closures are resulting in a stable reduction of entanglement risk in the southern Gulf of St. Lawrence snow crab fishery with no significant differences in the effectiveness between protocols. But they are only effective when whales are present and where there is co-occurrence. And finally, there's still more work to be done. Currently, we only have 4 years worth of data, and while our results present a strong case, this is a limiting factor, especially as we are seeing some variability that seems to be linked to the distribution and movement of whales. Future improvements should investigate considerations such as whale residency and habitat use, the compounding effects of displaced gear, and incorporating other fisheries into these assessments to start looking at cumulative impacts and the risk reduction contributed by these other fisheries. With more time, we'll be able to make an even stronger estimate. So we're grateful to our funders, the Canada Nature Fund and Pew Charitable Trust that support this research. Thank you for listening to my presentation, and I look forward to hearing your questions and chatting with some of you at this year's meeting.